We are going to discuss electrothermal atomic absorption spectrometry today, maybe for the next 2-3 classes also. And what I want to tell you about this electrothermal atomic absorption spectrometry, it started as a small modular attachment to the atomic absorption, flame atomic absorption, but now it has grown into a full-fledged analytical technique itself by its own merit. And we have discussed hydride generation, flame atomic absorption and cold flame atomic emission and cold vapor mercury as modular attachment for atomic absorption. Now we are going to discuss electrothermal atomic absorption spectrometry. Even though now it has become a full-fledged analytical technique by itself for parts per billion and parts per trillion level detection of the metal ions, the basic idea is only to ensure that maximum atomization takes place in the optical path of the atomic absorption spectrometer. That means, what we are going to do is we are going to develop a small piece of equipment where to heat the to provide heat for sample vaporization instead of the flame. That means, if you remember the design of atomic absorption schematic diagram, in place of flame and nebulizer we are going to put one heater. That's it basically. So, what difference it makes to the detection limit? That is a very curious point. Now, look at this slide. What we want to say is using flame atomic absorption, we need to use nebulizer. I had if you remember our earlier discussion on nebulizers, I had told you that about 13 to 20% of atomic of the sample solution gets vaporized and forms an aerosol, and then the aerosol gets carried away with the oxidant gas and flame oxidant gas and the acetylene gas. Okay. Now, it means that atomic absorption analysis using flame atomization, you are bound to use the sample as a solution, because you have to form the aerosol. So, for the analysis of solids in parts per million level, bringing the sample in solution itself involves a dilution, so that the concentration of the sample in ppm will go to parts per billion level. Suppose you get a small quantity of the sample, let us say about 0.5 gram, you dissolve it in 100 ml, 0.5 solid sample is 0.5 and dilution is 100 ml. That means the detection limits gets pushed, the analytical demand on the sample is more. You cannot dissolve 10 grams or 15 grams for chemical analysis. Many times you will not get that kind of samples. Suppose you want to do body analysis, how much blood you can take for analysis? A few milliliters or a few milligrams, right. So, you can't take 10 grams of blood sample and try to analyze the sample, it is not worth it. Same thing is true with respect to milk powder and food samples, tissue samples, you can't get too much sample also. From environment, you want to analyze the dust. For 24 hours if you run the sample collection, you may end up with a few milligrams of the total dust. Out of that you want to determine how much of nickel is there, how much of lead is there, etc. So, in the solid, if you want to analyze solid samples, dilution is a challenge, because dilution pushes the analytical limits to parts per billion level. So, the limit of detection for particular element is directly proportional to the concentration of the atoms in the flame. This is understood because the limit of detection will always depend upon the concentration of the sample in the flame. The more sample I have in the flame, the more better it will be detected. So, that means it is further dependent upon the flow rate of the solution, how fast we or how slow we let the aerosol enter the solution. So, the flow rate of the both oxidant and acetylene gas are very high, of the order of about 6 liters per minute and 3 to 4 liters per minute range. The time spent by the free atoms in the flame is very short. That time we can calculate, and it comes to about 10 raised to minus 4 seconds. So, from the nebulizer to the into the flame and out of the flame, the total time spent by the aerosol particles is 10 raised to minus 4 seconds. Within that time, all the reactions that I have described earlier must take place, form ions. Ions have to react with electrons, and then they should form atoms, and those atoms should get excited and reabsorbed, and all that processes has to take place. So, increase of free atoms by higher intake of the sample is not possible. It is restricted by the burner design. Once you make a design, you are fixed for that flow rate. You cannot change the flow rate too much anyway. So, it causes a deterioration of flame stability. For example, instead of 3 ml per minute, if you increase the sample flow rate to 6 ml, let us say double, then what happens? More aerosol, more liquid will move into the flame, and flame may get put off. You can't increase it to 12 ml or something like that. And the flame temperature will come down because we are introducing more liquid into that. 99% of the time the liquid is water or acid solution. So, these water droplets reduce the flame temperature. So, that also the reduction of flame temperature causes a deterioration of flame stability also. Flame may flicker, it may put off, again you have to light it, all those kinds of attendant problem will be there. So, people thought all these factors tend to limit the atomic concentration in the flame, atomic concentration. That means, detection limit also is rather limited. So, it leads to significant reduction of sensitivity also. Therefore, when the sample size is very small, let us say 5 to 10 microliters, it is necessary to work at absolute detection limit. We have only 5 to 10 microliters, 1000 microliter is 1 ml, right. So, 5 to 10 microliter sample like blood, tissue, brain samples, etc. if you get, it is necessary to work at the absolute detection limit only, that is expressed as micrograms, absolute. Therefore, non-flame atomization methods have been investigated to overcome these problems. So, why non-flame methods? Because if I heat a substance in an enclosure, convert it into vapor, 100% vaporization takes place instead of 20% of nebulization through that nebulizer and flame. So, people thought why not we introduce solid itself and then into the flame, and then let us see how the detection limits are obtained. So, people made boats, they took the sample in a small cup made of tantalum, introduced that cup into the flame by holding a tweezer or something, the fork. So, the solid sample itself gets vaporized 100%, not all the samples anyway, but attempts have been made. So, the people made small cups of tantalum, because tantalum is a material which can be obtained in a very pure form, and then it will not form reaction, it will not form compounds with other metal ions. So, tantalum is rather inert. People have tried platinum also, that is also an inert element, inert metal. So, take the sample in a platinum small crucible of about 2 mm, maybe about 10 milliliter, 10 microliter capacity, put the sample in that, and then you can evaporate it. So, several techniques based on the application of electron bombardment, flash method, flash evaporation, laser and plasma have been tried, but they have not gained popularity except the heating method, electrochemical heating. So, you can say that the idea was to put the sample, whether it is liquid or solid, in an atmosphere which can be heated electrically. There we put a small amount of the sample, and when we heat it, all the sample gets evaporated and form the vapor cloud. Okay. So, there the atoms are also available and electrons are also available. So, there will be, as usual, there will be a formation of free atoms and atomic absorption can take place. So, among all these attempts, Labov and later Mossman, two scientists, they designed an electrically heated graphite tube based on the volatilization of the sample by direct heating of the graphite cuvettes. You take a graphite cuvette, put it in the graphite cuvette, and then put it in the introduce the cuvette into the flame. So, they found out that with low voltage and high current in argon atmosphere, they could get detection limits of 10 raised to minus 12 to 10 raised to minus 14 grams per liter. That is less than parts per trillion, whereas in flame it is parts per million. Okay. So, the technique has evolved into a very powerful technique, graphite furnace, and this is known as electrothermal atomic absorption spectrometry. What they do? They take a graphite tube and heat it electrically, insert it into the path of the flame. So, then you put the sample inside, heat it, and then convert make the atomic absorption measurement as usual. So, in the Labov design, graphite tube is mounted in a chamber filled with the argon at reduced temperature, reduced pressure. The sample is deposited in the graphite cuvette, as I told you, volatilized and atomized by Joule heating, and that is resistance heating at 3000 degrees centigrade. I can heat it to 2000, 2500, 3000, anything, because graphite can be heated to very high temperature without destruction, okay, because it is a conducting material, it does not burn when you pass electric current, but temperature can develop. So, Labov obtained typical detection limit of 10 raised to minus 12 to 10 raised to minus 14 grams with this design. Labov is a Russian scientist and Mossman is an American scientist. I had opportunity to interact with both of them during the development of this graphite furnace, and I had the pleasure of working with them also. The graphite furnace developed by Labov is slightly complex and cumbersome in operation actually. So, that is why that design was later discarded by commercial manufacturers and then switched over to Mossman. But Labov is the father of electrothermal atomic absorption spectrometry. So, this is the Labov's argon chamber. So, what happened here? You see here two small electrodes and a small tube here. Look at my laser pointer. There are two electrodes and a small graphite tube here, okay, where my laser is sitting, laser is pointing, and these are the guide pins, and this is the base plate, and then this is the cover for this. So, this cover moves and sits exactly in this, so that it does not disturb the touch this graphite tube. Okay, it is just basically a small chamber, circular chamber, which is airtight. Okay. So, this is the Massman design, and this is the Labov design, and because it has to every time you have to open it, close it. See, this one, every time you put the sample in this tube, you have to close it, open it, close it, open it for after each measurement, etc. There is some slight amount of cumbersomeness is involved. So, what happened was, later Massman constructed a simplified graphite furnace in which the tube was continuously flushed with argon to prevent oxygen interaction with graphite. When you do not pass the oxygen, graphite will not burn, fundamental truth. So, but because of continuous flushing and slower rate of heating, the detection limits were 1 or 2 orders of magnitude lower than Labov. So, here the point is, in Massman design, argon is Massman design, argon is continuously flushed through the tube, whereas in Labov design it is just total argon atmosphere. So, because argon is continuously flushed through the tube, the atomic vapor gets carried away out of the system, just like in flame. In flame, what happens? The particles themselves are moving, aerosol particles. They move out of the flame and optical path. Here we are passing argon and pushing out the vapor. So, the detection limit in Massman design are slightly lower than the Labov design. Nevertheless, because of its simplicity and ease of operation, most of the graphite furnaces in use today are based on the Massman design, that is, they are tube furnaces with resistance heating, which offer flexibility in the programmability and operating convenience. I will show you the Massman design here like this. Here the brown one, reddish brown area which I am pointing is the graphite tube. There is a small hole here, and through this hole we put the sample inside the tube where my laser is sitting now. Okay. And this side, the graphite tube is cylindrical and it is open at both ends, so that I can pass argon like through this hole, and then it comes out and goes out, and the sample is either pushed through this way or it will go through, but this is closed. So, the only way the sample aerosols get out is through this. That means there is a more possibility of spending more time inside the graphite tube, and these two 1, 2, 3, 4 the surroundings are steel flanges, and these are the graphite tube. This is a plastic insulator and all that, and these are the heating plastic insulator here, and these are the graphite connectors for electrical requirement. So, what we have here is, I have a graphite tube which is fixed to the bottom of this bottom part, and the top part opens and closes the graphite tube. Okay. So, once I open this, put my sample, and then let the system run through and determine the atomic absorption reading as usual. So, this design 99% of the atomic absorption spectrometers are employing this design nowadays, and it is good for routine analysis. So, the tube is mounted in the optical path of the resonance line in such a way that the beam encounters only the atomic cloud unhindered by the tube geometry, because it is open at both ends. The rest of the instrumentation is same as that of flame atomic absorption, except the software which has to handle several other tasks that are typical of a dynamic signal. So, this we will explore now. So, what we mean is, we introduce the sample into a graphite furnace. The sample size can be 5 to 100 microliters. That means you have to use a micro pipette here, you cannot use ordinary glass pipettes. So, it is volatilized and atomized, and that leads to an absorption versus time signal, which resembles a gas chromatography peak. It does not give you a line peak, peak height is not very good. So, it gas chromatography like peak lasting a few seconds. That means, the shape of the curve is dependent upon the total number of atoms injected, residence time of the atoms in the optical path, and response time of the detector. Either the peak height, you can, if the peak is very uniform and very sharp, you can use peak height, or if it is not peak height, you can use peak area. The units of peak area are absorbance seconds. That means, in the calibration curve, we plot absorbance seconds versus concentration. So, the peak area or peak height we can measure as a function of concentration, and the latter being more suitable for routine and applications. Why? Because peak area takes care of the dynamics of the situation. That means, the sample may volatilize slowly, it may not volatilize slowly, and the peak area may shift a little bit this side that side depending upon our heating program. So, that this we have seen in hydride generation. I have shown you some of the peaks which are very sharp, some of the peaks which are not so sharp. The peaks which are not so sharp, we have to use peak area, that is absorbance seconds as the measurement unit. Okay. So, in 99% of the instruments, both peak area and peak height are measurable. You can choose either way depending upon the type of the signal. So, what are the graphite tube characteristics? What kind of graphite tubes we should be using? For a good signal, the graphite tube should be as long as possible, because the longer the tube, more would be the vapor it can hold, as simple as that. Okay. And it should be as narrow as possible. The hole should be as narrow. Normal dimensions of the tubes should be such that the whole tube should have uniform temperature throughout its heating area, but this is seldom the case. Apart from good geometry, the tube material and surface characteristics are very crucial in electrothermal atomic absorption. It is well known that at high temperature, graphite surface is highly permeable to metal atoms. What does it mean? So, if I take the metal sample inside the graphite tube, okay, if I take the metal inside the graphite tube, metal solution inside the graphite tube at high temperature, the metal may diffuse into the graphite material rather than form atoms and go out of the system. That is required in the atomic absorption, whereas at high temperature graphite surface itself can absorb the metals. So, this is another problem, but it has been overcome using various techniques which we will be discussing shortly. And optimum dimensions of the tube, these are the this is the dimension of the tube. L is the length of the tube, this is the angle through which the sample is introduced somewhere here, and this design is, this is the graphite tube. It is open at both ends where I have written D, and then here also it is open at D, and this is the sample where it is put. The sample is put here below the B like a blob through a micropipette, and the optical path radiation comes like this and then goes out like this. Okay. This length is about 3 to 3.5 centimeter, okay, and this D, the distance is about 5 mm maximum, 5 millimeters, 0.5 centimeter. So, it is a 3.5 centimeter long and 0.5 mm diameter in the Labov design as well as in Massman design. The sample is put here and electrothermized. Okay. So, attempts to prevent the permeability, we are talking about the permeability of the graphite surface at high temperature. So, people thought, why not we use tubes made of tantalum or molybdenum or tungsten. So, they use, you coat them, coat the graphite tube with a tungsten salt, tantalum salt, molybdenum salts, and the first you close the pores, then you put your sample. The sample will not permeate. This is one way of doing it, and this resulted in better sensitivity and reproducibility. See, in graphite furnace, whenever we are doing atomic absorption, sensitivity and reproducibility is a very important factor. Every time you do the operation, you should get the same reading, no? And that is something to do with precision and accuracy, right. So, precision should be good, accuracy also should be good. This problem was how we solve the problem of permeability. We attributed it to the sealing of the cracks and defects in the graphite furnace, because the graphite surface, a tube also, is a surface basically, and they thought that whatever is permeable material, if I put some amount of tantalum salt, it will coat the pores and then no more permeation is possible. So, Labov found that tubes made of pyrolytic graphite had the same properties. This is Labov's contribution to the electrothermal atomic absorption, and what he did was he coated the graphite tube with a dense, hard, impermeable, oxidation resistant pyrolytic layer of carbon of about 30 to 50 mm. He found out that such carbon tubes are highly resistant to oxidation and permit the determination of refractory elements also with high sensitivity, because we know that refractory elements are not easy to determine in flame atomic absorption, but in graphite furnace, if I use a pyrolytic graphite coating, then I can get better detection limits. Okay. So, this is the surface of graphite surface. Essentially it is a carbon surface. This is a normal graphite tube. Okay. Now, this one is a pyrolytic graphite tube, the one on the right. So, you can see the surface of this tube is much more rougher than the pyrolytic graphite tube, because it is very smooth compared to this. These are the SEM pictures, travelling microscope pictures of the order of about 10 micrometer. This is also 10 micrometer, this is also 10 micrometer area photographed through SEM, and you can see that this surface is much smoother than this surface. That means this has more cracks, sample can permeate through the cracks. Here it is not possible for the sample to permeate inside the surface. Okay. And then if I cut this pyrolytic graphite tube, now what I have here is in the bottom portion of this tube, it is normal graphite tube like structure, whereas on the top it is very smooth black carbon black area. In the bottom it is just like normal carbon, and there is a permeation coating, and then above that impermeable coating also of the same carbon atom. That means the heating can be carried out much more easily, simpler with this type of material. Okay. So, what are the system considerations we require in electrothermal atomic absorption spectrometers? So, one thing is, it is important to use argon in electrothermal atomic absorption. This is known as purge gas. That means you have to keep on using argon throughout the operation. Whenever you are measuring or performing atomic absorption, argon should be used, because argon is an inert material, it will not allow the sample to oxidize. That is number one. But it also functions several other functions. What are they? First thing is, being inert, it prevents the ingression of atmospheric oxygen. Atmospheric oxygen does not enter the graphite tube. That means oxygen is not available to burn the graphite. See, if oxygen comes, burning can take place. If argon is passing through, there is no oxygen available to the graphite tube. So, it prolongs the life of the argon tube, carbon tube. Secondly, it prevents metal atoms reacting with atmospheric oxygen to form refractory oxides, because it is a carbon atmosphere, carbon surface. Atmospheric oxygen is not there, that means refractory oxides cannot form. So, if the refractory oxides form, they reduce the sensitivity. Here there is no chance for oxygen to enter, so sensitivity remains high. Thirdly, it physically transports the matrix components out of the radiation beam before atomization, thus eliminating much of the background radiation. This point requires a little bit of explanation. What happens is, if I can heat it before atomization to about 400 degrees centigrade, water will evaporate, organic substances will evaporate and burn, etc. So, first if I heat it to 400 degrees with argon passing, whatever comes out of the system, acid vapors, this, that, and all those things will be swept away before measurement. That is one of the plus point of electrothermal atomic absorption, and it is a merit, it is the advantage. So, once most of these things are gone, what remains would be the metal, only the metal, not even metal oxides, maybe metal chloride to some extent, chloride, sulfates, etc. But in the carbon atmosphere, the metal salts get reduced to metals. Very simple fundamental truth. If you want to bake any metal, put a little bit of carbon into any salt and then heat it. Most of the jewelers do that. They take gold salt and things like that, and then add a little, heat it in charcoal, along with charcoal gets reduced to the metal. So, it is a very well known metallurgical procedure also. So, it physically transports the matrix, basically it physically transports the matrix component out of the graphite tube before atomization, so long as argon is flowing. So, it is also possible to precisely control the flow of organic gas or even reduce it to 0 during measurement to obtain better sensitivity. So, now the point here is, so long as I use organic argon, the materials whatever produced from our sample gets swept away. Now, when I want to make a measurement, I can stop the argon flow and the atomic cloud that forms inside the tube will not move. It has to move only through diffusion, because if I stop the argon flow, atomic cloud will be held longer inside the tube. That means I can make the measurement for longer time. So, this is one of the most important aspect of electrothermal atomic absorption. So, system consideration is we need argon for preventing the ingestion of oxygen into the graphite furnace, prevent the oxidation, physically transport the material out of the graphite tube. At the time of measurement, argon should not be there, only the metal vapor should be there. We will discuss about the temperature control. We can do it in the next class.